This PowerPoint goes along with the example problems that we have for moment of inertia. First problem says three particles are located in a coordinate system shown in the figure. Find the distance of the center of gravity from the origin. So basically what we're going to do is we're going to find the center of mass or center of gravity in the x direction, the center of gravity in the y direction, and then that's going to give us our xy coordinate that we're going to find the total distance from the center of mass from the origin. Alright, so that center of mass in the x direction, it's going to be mass 0 and mass 2 are both at position of 0 in the x direction, and then mass 1 is at 3 meters in the x direction. If you remember the center of mass equation, to find the center of mass, it's the total mass times distance from the origin, adding all those together, divided by the total mass of the system. So we got mass sub 0, x sub 0, plus mass sub 1, x sub 1, so on and so on. And since the mass sub 0 is at a 0 position, and then mass sub 2 is at a 0 position in the x direction, then those are going to be 0. And then mass sub 1 is 3 meters. So we go ahead and figure out the top, that's 9, and then the bottom, the total mass is going to be 14.5. So the center of mass in the x direction is going to be 0.62. So we're going to do the same thing in the y direction, except this time we have mass sub 0 and mass sub 1 has 0 in the y direction, and then mass sub 2 is 4.5 meters in the y direction as stated right here in the prompt. So we take the same equation except for the y direction. We go ahead and add all these together, and mass 2 is the only object that has a distance from the origin, so that's the only one that has anything other than 0 for the distance, and then we take that and get 29.25 divided by 14.5, and we find that the center of mass in the y direction is 2.02. So now we have these two positions. We have the x position and the y position. So we're going to take these two and we're going to determine the distance from the center, or from the origin, the center of mass. The distance is going to be basically the Pythagorean theorem. The x and the y give us coordinates so that we can find the hypotenuse, the total distance from the origin. So square root of 0.62 squared plus 2.02 squared, and that's going to give us a total distance of 2.11 meters of the center of mass from the origin. Question number 2 says a constant torque of 19.7 newton meters is applied to a grindstone of which the moment of inertia is 0.114 kilogram meters squared. Find the angular speed after the grindstone is made 12.8 revolutions. Assume the grindstone starts from rest. So the net torque is going to be equal to the moment of inertia times the angular acceleration. To find the angular acceleration, we need to take the total torque and divide it by the moment of inertia. Well, we have the total torque. That's going to be 19.7 divided by the moment of inertia, which is 0.114, and we get that the angular acceleration is going to be 172.8 radians per second squared. Now the change in angle is going to be 12.8 revolutions, but that is not in base units. We've got to get that in radians. And the conversion for revolutions to radians is going to be 2 pi radians is one revolution. So we multiply by 2 pi to get that we have 80.4 radians for the total angular displacement. So we got the angular displacement, we got the angular acceleration, and we need to find the final angular speed. We have the initial angular speed because it starts from rest. So to find the final angular speed, we go ahead and plug in all the information we know. We got 0 squared plus 2 times the angular acceleration, 172.8 times 80.4, and we find that our angular velocity is going to be 166.7 radians per second. Number 3 says 2 pulley wheels, one of radius 0.32 meters and the other of a radius 1.3 meters, are mounted rigidly on a common axle. So they're both going to be spinning around the center right here. This one is going to have a radius of 0.32, and this larger one has a radius of 1.3. The rotational inertia of the two pulleys, which are clamped together, so they don't move at different speeds. They both are going to be moving together. It's going to be 1.5 kilogram meters squared. A mass of 17 kilograms is attached on the left side over here, and on the right side is going to be a 6.6 kilogram mass. So we need to find the angular acceleration of the system. Well, we've done problems like this before, where we have two objects that are going to be pulling opposite directions. So we have to figure out, basically we're going to run a system of equation for this, a system for this, and a system for the pulley itself. For the mass 1, we're going to draw a free body diagram. We got force of tension pulling upward and force of gravity downward, and we're going to assume that it's accelerating downward. Now, I don't really have a good basis to determine whether it's accelerating because this over here has a larger mass, but it has a smaller radius. So even though it has a larger mass means more force of gravity, which means more torque, but it has a smaller radius. So I don't really know which torque is going to be greater. Now, it doesn't really matter which way it's going to accelerate as long as I pick a direction and then I'm consistent from that point forward. So I'm going to say for this one, the acceleration is going to be downward. So that means the force of gravity 1 minus the force of tension 1 is going to be equal to mass times acceleration. I'm going to say down is going to be the positive direction for this because it's more convenient and my acceleration is going to be in the positive direction. We're going to plug in what we know. We got mass 1 times gravity. That's 17 times 9.8 minus the force of tension 1 is going to be equal to the mass, which is 17 times the acceleration. We get 166.6, and to find the force of tension, we take everything else to the other side, and we get 166.6 minus 17 times the acceleration. The second free body diagram, this mass, since we said that the mass over here is going to be accelerating downward, then that means that this one has to be accelerating upward. So we're going to say that the upward direction is going to be positive. So that's force of tension 2 minus force of gravity 2. That equals mass 2 times acceleration. We go ahead and plug in our numbers, and we get that force of tension 2 minus 6.6 times 9.8, which is 64.68. That's going to be equal to 6.6 times acceleration. Take that to the other side, and we get our force of tension 2 equals this. Now we have three unknowns. We got force of tension 1, we got acceleration, we got force of tension 2. So we basically need to come up with another equation with this pulley right here in order to determine what the acceleration is going to be. Now in this process, we're actually trying to find the angular acceleration. So the linear acceleration, we actually have to convert that over to angular acceleration. So the way we do that, we got force of tension 1 over here, force of tension 2 over here, and the acceleration is going to be this direction. Since we said that the acceleration is downward for mass 1, then that means it's going to be a counterclockwise rotation, counterclockwise acceleration, which we're going to find as a positive acceleration. So force of tension 1 is going to be equal to 166.6 times 17 times the angular acceleration times the radius, which for force of tension 1 is a smaller radius, and that's 0.32. For force of tension 2, it's a larger radius, so it's going to be 1.3. And we go ahead and take the 17 times 0.32, and we get 5.44. We take the 6.6 and multiply by 1.3, and we get 8.58. So this gives us our equations in terms of angular acceleration. So we go ahead and set those equations aside, and our net torque is going to be equal to the angular inertia, or the rotational inertia times the angular acceleration. The torque is going to be provided by these two forces that are going to be tension 1 and with its radius minus tension 2 with its radius, because tension 1 is the counterclockwise direction and tension 2 is the clockwise direction. So we go ahead and plug in what we know. Force of tension 1 is this equation right here. So we got 166.6 minus 5.4 times the angular acceleration times radius 1, which is 0.32. And then this equation right here, which is 64.68 plus 8.58 times the angular acceleration times its radius, which is 1.3. And then the angular the angular inertia is going to be 1.5. So we have that there. Alright, so we're going to distribute this 0.32 to both of these. We're going to distribute this 1.3 to both of these terms, and this gives us this equation right here. We're going to combine like terms. We've got the 53.3 and the negative 84.1, and then we also have the negative 1.4a alpha and the negative 11.2 alpha. And we go ahead and combine those, and then we got the 1.5 times angular acceleration over here, so we need to bring this negative 12.94 to the other side, and we figure out that we have negative 30.8 is going to be equal to 14.44 times the angular acceleration. That gives us angular acceleration of negative 2.13 radians per second squared. Now what this negative means is this negative says that the angular acceleration is actually in the opposite direction from what we expected. So it's actually not going to clockwise or go counterclockwise, it's going to rotate clockwise. So it's just in the opposite direction of what we expected, and that's okay as long as we understand that if we're consistent the entire way, the final answer is going to tell us what direction it actually is. Alright, so part B says find the tension in the cord attached to the 17 kilogram mass, and part C says find the tension in the cord attached to the 6.6 kilogram mass. So we're going to use our two equations. We're going to go ahead and plug in our angular acceleration into the first one. So we get force of tension is going to be equal to 166.6 minus 5.44 times a negative 2.13. And again, we know that it's going to be clockwise, but we're going to go ahead and put that negative in there because that's the answer that we got for our acceleration. We need to be consistent with that. So we plug that in, and you get a force of tension that's going to be equal to 178.2 newtons. And then for part C, we go ahead and plug in our angular acceleration there, and we get a total of force of tension of 46.4 newtons. Number 4 says a weather vane consisting of a rooster sitting on top of an arrow is sitting on top of a garage. The vane is fixed at on a vertical shaft with a radius of 0.0157 meters. So what that's saying, that's the radius of this little part right here that the rope is going to be pulling on. So we got the radius there for the in order for us to figure out the torque. And then that's free to turn as shown in the figure. And the student sets up an experiment to measure the rotational inertia of the rooster and the arrow. The string is wound around the shaft and passes over a pulley and is connected to a 2.04 kilogram mass hanging over the edge of the roof. Now this pulley right here, we're going to assume that that pulley doesn't have much moment of inertia, that it's not going to take too much energy or too much force to get that to turn. So we're going to ignore the effects of this pulley right here, but we're just going to concentrate on the rooster and arrow. So when the 2.04 kilogram mass is released, the student determines the time, t, that the mass takes to fall through a distance of 0.307. So find the rotational inertia, I, if the rooster and arrow if the time is going to be 11.8 seconds. So I have a distance that is going to be falling. I have a time that's going to be falling also, and I know my initial velocity is going to be 0 because it's released from rest, so I can use that in order to determine how much acceleration that it's going to have. So displacement is going to be 0.307, and then the acceleration, and then we got the time, which is 11.8, and then the initial velocity is 0. So we rearrange this to find the acceleration. This part's going to cancel out, so we divide by, or actually multiply by 2 and then divide by the time squared, plug in our numbers that we know, and our acceleration is going to be 0.0044 meters per second squared. Okay, so now how do we use this to find the angular acceleration? Well, in order to do that, we got to take the net torque is going to be equal to the angular inertia times the angular acceleration. Before we do that, we got to figure out how much the force of tension is going to be. So we got force of tension upward on this mass, and we got force of gravity downward, and the acceleration is obviously going to be downward on this one. So we're going to do our force of gravity down. That's going to be in the positive direction. Since the acceleration is downward, we're going to make that positive. Minus the force of tension is going to be equal to mass times acceleration. So we plug in the force of gravity as mass times the acceleration due to gravity. And then we got 2.04 times 9.8 minus the force of tension is going to be 2.04 times 0.0044. And we get 19.99 minus force of tension. And then we find the force of tension is going to be 19.98 newtons. All right, so that gives us our force of tension. We can use that force of tension times the radius in order to figure out the net torque that's being applied. And then we can use the acceleration in order to find the angular acceleration of the rooster. So we got the net torque equals the moment of inertia times the angular acceleration. Go ahead and plug in what we know. We got force of tension times the radius is going to be equal to the moment of inertia times the linear acceleration divided by the radius. That equals the angular acceleration. So we take it to the other side in order to figure out the moment of inertia. So force of tension times the radius squared divided by the acceleration. Plug in our numbers, and we get a moment of inertia of 1.12 kilograms meters squared. All right, number 5 has a solid steel ball of radius 0.152 meters and a mass of 3.85 kilograms. It's rolling down a 12.5 degree incline without sliding. So what is the linear acceleration of the ball as it's rolling down the incline? Well, in order to figure out the linear acceleration, we got to figure out how much it's going to be rotating. So we got a net torque that's going to be equal to the angular, the moment of inertia times the angular acceleration. We have a force of friction. That's what's going to cause it to rotate. Think about this. If we didn't have friction, then this thing would just slide down and not rotate at all. Friction is actually what's causing it to rotate. So the force of friction times the radius, that's going to be the torque that's being applied in order to rotate it. It's going to be equal to the moment of inertia. The moment of inertia is a k value times mass times radius squared. That's going to be multiplied by the angular acceleration, which is the linear acceleration, divided by r. And a linear acceleration is actually what we're trying to get at. Remember, k value for a solid sphere, for a solid ball, is going to be 2/5. So we're going to plug that in a little bit later. All right, so the radius here is going to cancel from the bottom to the top, and then the radius on each side is also going to cancel. So that gives us our force of friction is going to be equal to k times mass times acceleration. Now, if we draw a free body diagram, we figure out that the net force, we got a force of gravity pulling down the ramp. That's the parallel component. And then we got force of friction up the ramp. Those two are going to be pulling against each other, and it's going to cause a total acceleration of the ball rolling down the ramp. So the parallel component pulling down the ramp minus force of friction equals mass times acceleration. The parallel component of gravity on a ramp is going to be the sine component. So mass times gravity times the sine of theta is going to be equal to the parallel component, and then we subtract the mass acceleration, because here we took the force of friction to the other side to make it positive, and then we had to subtract mass times acceleration. So that gives us our mass times gravity sine of theta minus mass times acceleration. Factor out the mass, and we go ahead and figure out that these two forces of friction are equal to each other, so we go ahead and set them equal to each other. And then we see that the mass is going to cancel out, so that gives us our k value times the acceleration is going to be equal to the acceleration due to gravity times sine of theta minus a. And we go ahead and plug in our numbers. We got the k value for a steel ball for a solid sphere is going to be 2/5. That times acceleration is going to be equal to 9.8 times sine of 12.5 minus the acceleration. And we're going to bring this acceleration to this side, so that gives us 2/5 is 0.4 times acceleration, then plus the acceleration here, which, by the way, the coefficient in front of this is going to be a 1, so 0.4 plus 1, and that's going to give us equal to 2.121, and that's the 9.8 sine of 12.5. So we have 1.4 over here. We divide both sides by 1.4. We figure out our acceleration is going to be 1.515 meters per second squared. Second question asks, what's the minimum coefficient of friction? Well, coefficient of friction is going to be equal. That's the force of friction is going to be less than or equal to the coefficient of static friction times normal force. So in order to figure that out, we got to first figure out the force of friction. So we use this equation right here, which we actually could have used either one. It doesn't really matter, but this one has a trig function in here. This one just looked easier to use, so I chose that one. 2/5 of 3.85 times 1.515. That's going to give us 2.33 newtons of force. And then the normal force is going to be equal to the perpendicular component. If you remember, the perpendicular component of gravity is balancing the normal force, so we figure out the perpendicular component is the cosine component. So it's mass, which is 3.85 times 9.8 times cosine of 12.5, and we figure out that that's going to be 36.8 newtons. So we get our force of friction is going to be greater than or equal to the coefficient of static friction times normal force, and that's we find our coefficient of static friction is going to be greater than or equal to 0.0633 in order to make sure that this doesn't slide at all. All right, so the next part says, assuming the ball is starting from rest, what is the final angular velocity of the ball after it rolls 4.28 meters along the incline? Now we're trying to find the angular velocity, but we have the linear acceleration. We also have the linear distance, and we know it starts from rest, so we have the linear velocity. So it's actually easier to find the linear final velocity and then use that to find the linear or the angular final velocity. So we go ahead and plug this in. We got final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Plug in our numbers. We find our final velocity is going to be equal to 3.6 meters per second. And then our angular velocity is going to be equal to the linear velocity divided by the radius. So that's 3.6 divided by 0.152, and that gives us an angular velocity of 23.7 radians per second.